Hi, my name is Charlie, and you can also call me the Guitar Boy. Today, we are going to be discussing the topic of atomic structure. Like we have on the board, this is atomic structure 8, and it is atomic structure 8 because I decided to divide the topic of atomic structure into simpler units in order for me to be able to cover the topic. How particles of an atom was discovered, by J.J. Thomson, Rutherford, and other scientists, Niels Bohr's mechanical models of an atom. You remember the orbit of an electron in Niels Bohr's model of an atom is identified by principal quantum number. Today I told you in our last video under uh, mechanical model of an atom that we are going to be talking about quantum number because the mechanical um, model of an atom introduced us to the concept of orbital. So now under wave mechanical theory, it is telling us that the the energy of an electron, even though we might have more than one electron here, we might have more than two electrons here, we might have any amount of electron here, that the electrons here are not do not have the same energy. Electron here in each energy level do not have the same energy, and what is responsible, how can we explain that electrons following the wave mechanical theory. However, wave mechanical theory told us, go and watch, if you can please go and watch the previous video, which is wave mechanical theory, wave mechanical model of an atom. Notice that electron does not revolve around the nucleus of an atom, that it is found in an orbital, a region around the nucleus where there is a possibility of finding electron. So, and the electron do not have the same energy. That the energy of an electron inside an orbital is identified by 4 quantum number. The energy of an electron in an orbital is identified by 4 quantum number. They are: 1, the principal quantum number, which is represented by n; the azimuthal or subsidiary quantum number, which is represented by small letter L; and we have magnetic quantum number, which is represented by M. We also have the spin quantum number, which is represented by what? S. So, which is represented by S. So, to know the energy of an electron, even in a given principal quantum number, such as this share, maybe you have 2 electrons here, you have 3 electrons, maybe this is one orbital, just like that. You have it. To know the energy of electrons, you will not just use this energy level alone. There are other energy subdivision inside this energy level that makes the energy of this electron to be different from the energy of this electron to be different from this energy of electron. So no 2 electrons inside this atom would have the same energy. We are going to talk about that later. We are going to talk about that. No 2 electrons will have. Why? Because the energy of an electron is not only affected by this principal quantum number, rather it is affected by this other quantum number. So we are going straight to explaining the explanation part now. Principal quantum number. This has an integers. It has an integer. An integer is a number that is not continuous, such as what? 1, 2, 3, 4, just like that till infinity. This has an integer that ranges from 1, 2, 3, 4, just like that. And this one represents K chair, just like I drew those cycles just now, K, L, M, K, L, M, N. So just MN, if you have 5 here, O, just like that. So that's what it represents. 1, K represent 1, L represent 2, M represent 3, N represent 4, O represent 5. Now to know that will now move us to get to know the maximum number of electrons that can enter here. The maximum number of electrons that can enter the K shell, that is this first shell, this is the nucleus, the second one, the third one, the maximum number of electrons that can enter only here. We want to calculate it now. We also calculate the maximum number of electrons that can enter this energy level, the maximum number of electrons that can enter this energy level. You know, this one represents this one represents this one represents this one. If you draw another cycle now, this one will represent that cycle, just like that. So the maximum number of electrons that you can find in any of this energy level, you use this formula to represent a 2n raised to power 2. You remember n is the principal quantum number. Now, which means when the principal quantum number is 1, it will not be, to calculate the number of electrons, it will not be n times 1 raised to power 2 equal to, you know, first you simplify what is here first before you multiply it by what you have here. 1 raised to power 2 is equal to 1. 1 times 2. 1 raised to power 2 means 1 times 1. 1 raised to power 3 means 1 times 1 times 1. 1 raised to power 4, 1 times 1 times 1 times 1. So just like that. So this one is 1 raised to power 2, which means 1 times 1 is equal to 1. So 1 times 2, which is what? 2. So the K, when n is 1, which is K share will carry a maximum number of what? 2 electrons. So let's calculate for L share. The maximum number of electrons, which is 2 times 2, because L is 2, when N is 2, the maximum number of electrons, that's the highest number of electrons that can enter the L orbit. The L orbit is, the L energy level is 2 raised to power 2, which is 4. 4 times 2, which is 8. This is the maximum number of electrons that can enter. So the maximum number of electrons that can enter here will be what? That's the M energy level, or the third energy level will not be what? 2 times 3 raised to power 2, which is equal to 3 times 3, because 3 raised to power 2 is 3 times 3 is 9. 9 times 2, which is what? 18. The maximum number that can enter here is 18. You also come here 2 times 4 raised to power 2, which is equal to what? 4 raised to power 2 is 16. 16 times 2, which is what? 32. So this is the maximum number of electrons that can enter here, which means this one is 8. So if you think about it in that, which means whatever we get here are the sub energy inside here. Whatever we get here are the sub energy inside here. To calculate the number of orbiter in each energy level, we use n raised to power 2. Because, you know, to calculate the number of electrons in each energy level, we use, you know, we just finished using 2n raised to power 2 now. But to calculate the number of orbiter, you know, each orbiter carry 2 electrons. Each orbiter can only carry 2 electrons. To calculate the number of orbiters in each energy level, you use n raised to power 2, which will give us, the first energy level will not be what? N raised to power, will not be what? 1 raised to power 2, which would, the first energy level can only carry 1 orbiter, because 1 raised to power 2 is 1. The second energy level, which is 2, n is 2 raised to power 2, will not be 4, because in the second energy level, n is equal to 2. Then 2 raised to power 2 will not be what? 4. So it can carry 4 orbiter. 1, 2, 3 plus 1, which is the s orbiter. So just like that, if you use this formula, you'll be able to calculate the number of orbiter. In order for the video not to be too long, just use the formula, you'll be able to calculate the number of orbiters there. Now, these are what? For the principal quantum number. Okay. Now, for the azimuthal quantum number, for the azimuthal or subsidiary quantum number, azimuthal or subsidiary quantum number, it has an integers that ranges from 0, 1, 2, 3 to n minus 1. to n minus 1. You remember n is the principal quantum number. To n minus 1. N is the principal quantum number. It has, the essence of this is to know the energy of the electron right there inside the room, inside your room, from city to room. So the city will affect your energy. The house you are staying will affect your energy. The room you are will affect your energy. So this is why each electron has different energy, because everything affects, these things affect their energy. So this is how this principal quantum number affects their energy. So this zero is represented by S, just as this one represents K. This one is P, represented by P. This one is represented by D. This one is represented by F. So S, P, D, F. All these ones are sub-energy level, or the one we call orbital. S orbital, P orbital, D orbital, F orbital. So they are sub-energy level. Inside, this one is energy level, these are sub-energy level, which means they are found inside here. The energy level found inside, the sub-energy levels are found inside the energy level. Now we'll now move to the next one, which is the magnetic quantum number. Magnetic quantum number. Now this magnetic quantum number has an integer that ranges from -L through 0 to +L. -L through 0 to +L. The essence of this is to show us that, that even in the same room, we might have small rooms inside the same room, which will make the energy of the electron found in them to be different. Like for instance, in the master bedroom, you have toilets, you have the bedroom, you have the wardrobe. All these ones are found inside you classify them as the master bedroom. Everything is classified as one room. So those, in this case, for the purpose of this study, those room toilets, they are considered, I liken them to be what we call degenerate orbiter. Degenerate orbiter. They are just degenerate orbiter. We'll talk about the degenerate orbiter. So that room, even though it's one room, but it has different apartments. For instance, the energy you have when you are in your bedroom, your energy is different from when you are in your bedroom. Your energy is different from when you are in your wardrobe doing one or two things. Your energy is different. So the location of an electron affects the energy of that electron. So we are going to use this to know the different how magnetic quantum number tend to affect the energy of electron before we get to the final bus stop. So how do we use this? We want to know the number of orbitals, degenerate orbital. We want to know the number of orbitals the degenerate orbital each orbital can have. Like, as you can see, they say the magnetic quantum number ranges from a value, it has a value that ranges from -L through 0 to L. Remember, when L is equal to 0, look at L here, because L is the azimuthal or subsidiary quantum number. When L is equal to 0, you say -0. They say through 0, you write 0 through 0. That is, after -0, what's the next number? Is 0. After 0, what's the next number? +0, because they say minus L through 0 to +L. It will now be what? +0, because L here, which is the azimuthal quantum number, is what? 0. So in this case, if you check all the values here, they are all the same. If you check all the value here, -0, 0, and 0, they are all the same. Let's use something to just prove only this one, because I will only do it for just this video. Let's use a check to check that all these values here are 0. Let's add 2 to all of them, 2 to all the values here. 2 minus 0 is equal to what? 2. 2 plus 0 is equal to what? 2. 2 plus 0 is equal to 2. You see that all the number here are the same. That's why they gave you the same answer when you add them to 2. Okay? When you add all the numbers to 2, that's why they gave you the same value. So they are all the same. which means every number here you have to reason it to be 1. You assume they are just 1. Okay, you assume the number is 1, which tells you that since it does not have degenerate, since they are all the same thing, like I prove here now, it shows that this s orbital does not have degenerate orbital. This s orbital is just the same thing. So everything, all the values we have here, they are all the same thing. So it does not have degenerate orbital. So don't forget, mark the word degenerate orbital. We are going to use the word later in our next video. It does not have degenerate orbital. So it's just 1. So the s orbital, you write it like this, s orbital. You also come here for the next one, which is p. Okay, p is what? Minus p is 1, the p orbital minus 1, because minus L. We have talked about s of L. We want to talk about p of L now. So p, when p is 1, minus 1, after minus 1, you get to 0, then plus what? 1. After minus 1, you get to 0, then plus 1. It shows that p orbital has 3 degenerate orbital, because all the value here are different things. In that is bedroom, you have wardrobe, your bedroom, your toilet, and your just like that, depending on the atom. So now you see, since all these numbers are different, you say they have 3 degenerate orbital. 3 degenerate orbital. 1, 2. So this is p orbital. So we have 1, 2, 3 in p orbital. We have 3 degenerate orbital. So everything that was 1 here degenerates into 3. It was just p orbital. It degenerates into 3 orbital. Why? 1, 2, 3. 1, 2, 3. That is how it is 3. So minus 2. After minus 2, you get to minus 1. After minus 1, you get to 0. After 0, you get to plus 1. After plus 1, you get to plus 2. So that is it. Because they said minus L. L here is 3, right? Minus L through 0 to plus 2. Plus L. So you start with 2, because start with 2, end with negative 2 plus 2. Positive, negative L, end with positive L when you take when you take it through 0. So minus 2, minus 1, minus 0, plus 1, plus 2. So you now see that all the value here are different also. You can check it by adding them to 2 to the same thing I did here with the same thing I did here. You now count the number 1, 2, 3, 4, 5. You now see that this particular d orbital has 5 degenerate orbital. 5 degenerate orbital. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So d orbital has 5 degenerate orbital. You see it on the board. So the next one is what? F orbital. We'll stop there. F orbital, which the value is 3. You start from L. When L is 3, it will start with minus 3 and end with plus 3. Look at it, minus L to plus L, through 0 to plus L. You take it minus 3, minus 2, minus 1, 0, minus plus 1, plus 2, plus 3. So minus 3 through 0 to plus 3. This, all the values here are different. You can also check it by adding them to that 2, the way I did it here before. So when you do that, you are going to have 1, 2, 3, 4, 5, 6, 7. It shows that this particular orbital, which is the F orbital, has 7 degenerate orbitals, which are 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Now, that is why whenever you, this, again, I recap, S orbital has orbital, 1 orbital. It does not have degenerate orbital. It still remain 1. You have it here, 1, just 1. Still remain here. So, just S. Now, P now share itself, degenerate into 3 orbital, which means all these are not the same energy. They don't have the same energy. Okay? So if electrons are found, electrons are the things you are going to arrange here, because we are trying to know the structure of an atom and how electrons are arranged inside an atom. That's why we are doing all these things now. So coming to here, the same thing has this degenerate orbital. Coming to here, this also have degenerate orbital. So for each orbital, the maximum number each orbital can carry is 2. The maximum number of electrons each orbital can carry is 2. So this one can only carry two electrons. That is why when you are writing electronic configuration, maybe you would have seen something like this. First S, that is the principal quantum number S, has 2 electrons, because S orbital can only carry the maximum number of 2 electrons. Then when you have something like 2s, S must always be 2, because this is S orbital inside the principal quantum number 2. Then you have sp, this is p orbital inside the principal quantum number 2. Then p can carry maximum number of 6 electrons. Why? Because 1, 2, 3. We said each boss can carry 2, each boss can carry 2, each boss can carry 2. That's 2 times 3. That's 6. So p orbital can carry the maximum number of 6, unless the number of electrons remaining is not up to 6. Then you have 3s. 3s can carry 2. All s can only carry 2 number of electrons. Then you go to 3p. 3p can also carry maximum number of 6 electrons, because this is p orbital. It can carry maximum number of 6 electrons. That is p orbital inside the third energy level, or the third principal quantum number, inside the third energy level. So that all these numbers represent, this represents first energy level, second energy level, second energy level, third energy level, third energy level. And in this kind of, I just put this here so that you have insight of how you write your electronic configuration, so that you know that what we are doing here is not rubbish. Okay, now everything we are doing here now, we are going to use it later to write our electronic configuration later. And if you check, the highest energy level here is 3, and this will be the outermost energy level, the outermost shell that you usually hear, the outermost energy level. So the number of electrons here is the valency we are talking about, the valence electron, the number of electrons in the outermost, the biggest, the highest energy level. The outermost energy level is what? The valence electron. So note this. I'm trying to relate it to what we are doing now. That is what you now see, that magnetic quantum number help us to know the degeneracy of the electron, how many suborbital we have inside orbital. So all these ones now are suborbital inside this p orbital. These ones now are suborbital inside this d orbital. Okay, all these ones are suborbital inside this f orbital. So while as everything here, all these orbitals are also all these orbitals are sub-energy level inside this energy level. You now see that this one is found inside this one is found inside this. So this one is like a city, this one is like the room, the house, this one is like the rooms. Okay, so the rooms are found inside the house are found is the house is found inside the city. The rooms are found inside the house is found inside the city. So just like that, we move to the next one, which is what? The spin quantum number. The spin quantum number has a value. The spin quantum number, let me clean here. The spin quantum number has a value of plus half and minus half. This value here tells us how the electron tend to arrange itself inside an orbital, how they spin inside an orbital. I told you before that the maximum number of electrons each bus can carry is 2. So inside that bus we have 2 electrons. They will not spin in the same direction. The one will spin up, the other one will spin down. This one that spin up represents this plus half. This one that spin down represent this minus half. So the reason why these atoms tend to arrange themselves in this manner is because of this manner tends to enhance the stability of the atom itself. So when the electrons are arranged like this, they tend to enhance the stability of the atom itself. That is why they are being arranged like that. So if you also come here, depending on the number of electrons, which we are going to be talking in our next video when we are talking about the principle for arranging, in our next video, atomic structure 9, we are going to be talking about the principle for arranging an electron in an atom, that is in an orbital. So that's what we are going to be talking. So here will now be this one spine up, this one spine down, 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 this one spine up. I'm just doing. So in our next video, I'm going to do this appropriately, but I'm just trying to show you how the electron, how spine, I'm just trying to explain the spine quantum number, how electrons inside an orbital are arranged, how one will spine up, one will spine down. Thank you for watching this video. So thank you for watching. God bless you. If you are in Edo State, you are looking for physical classes, Total Ground Tutorial is the right place for you. We are here in Edo State. We are here in Edo State, Benin City, Sapele Road Bypass, Okanwa, close to Belesima Junction. Do well to come and join our physical classes. We will meet in our next video. Bye.